We're going to move on to a panel discussion, which I hope will be wide-ranging. And again, in order to save time, I'm just going to call up the panelists. So there's, over here, I see Terry Sejnowski. I see Tommy Poggio, Regina Barzilay, and Rodney Brooks. And if you'll just come up here, these are all very distinguished people that should be getting lengthy introductions, each one of them, but they'll have other moments to be introduced at greater length. What I thought we'd start with is just going from right to left. What's been left out so far this morning that you would hope to hear more about as things proceed over the next 2 days? So, Professor Brooks?
Oh, I didn't know that. I thought we had a different question.
Oh, okay. Well, if you prefer to start on another question, please go ahead, but announce the question.
I thought the question was what is deep... Did I read the wrong thing? Wasn't it what is deep learning not doing well? Was that the question?
Okay, if you want to do that, let's do that.
What I was told to think about. So I think we've seen some press about deep learning, a mixture of convolutional networks and reinforcement learning. And the headlines say we're learning to do dexterous manipulation. In reality, and Jitendra pointed this out this morning in his talk, a lot of what is really happening in manipulation is just a parallel jaw gripper. And there is some progress on that. It's being driven by the picking problem in fulfillment. So there's a real commercial push to be able to pick objects better so that they can be, put in your Amazon package and shipped to you. But these things that we have on the end of our arms are quite amazing. They evolved initially, as we came out of the water, and we had this five-way architecture just to push on the ground, and it's evolved into this complex hand. I don't believe that this mechanical thing is the optimal device at all, because of its evolutionary history was really restricted in what it could do, and came into this. There's probably much better hands. But the examples we see, such as OpenAI, was holding something like this and reorienting it, except it was a cube, and after 200 years of simulated time, it was able to move it around about as well as a person can when they're holding a cube this way, not that way, but this way. And that's really only a tiny, tiny, tiny little piece of what we do with our dexterity of our hands. And part of the problem is that we can't get massive amounts of data. They chose a problem where the cube had 6 letters on it, and so the convolutional neural network looking at it in simulation could estimate exactly the orientation of the cube. But using deep learning for more general dexterity, I think we're a long way from figuring out what tricks we would need in order to both collect data and in order to learn.
Professor Sejnowski.
Well, I'll take a crack at the new question. Okay, what I was expecting to emerge would be insights into this fantastic opportunity that we've gotten from the practical applications. There are these architectures now that are functions. They are functions, and we should be able to understand them mathematically. And I'll give you a story about how that unfolds. Back in, over 150 years ago, Joseph Fourier came up with this simple concept of having a series of terms that add up to a function. And the reason why he came up with that, he wanted to solve the heat equation. So it was a way of solving a partial differential equation. He thought that was very neat. All the problems he worked on were yielding solutions that before there were no analytic functions for. And so he submitted it to Compte Rendu, French math publication. It was rejected. It was rejected because the mathematician said, these are not functions. You have not proven convergence. Fast forward. Analysis is one of the jewels in the crown of mathematics. This is like it created a whole area of mathematics. And here we are today. We have these new class of functions. I mean, they have a lot more parameters and they're more complex perhaps, but not that complicated. We should be able to understand them. And it will probably give rise to new mathematics. I don't think that simply hacking away at it with current tools will necessarily reveal the black box. So I think that's really what I'm hoping will emerge from our discussion is how to proceed in that direction to be able to mine. I think it's a real opportunity for mathematicians, actually. It doesn't happen that often that you have a new class of functions.
So I'm not sure which questions were there, but I would say whatever I've prepared. And the question that I was thinking, we're all going randomly. And I missed the first talk, so maybe it was already discussed. But the question that I was actually thinking quite a bit recently when I was working extensively on an ACL paper, which I didn't manage to submit, was about human knowledge. And we are all thinking a lot about how does whatever our models learn about language, about chemistry, about any of the subjects really relate to our human understanding. So for those of you who've seen Chris Manning talks, one thing that was really striking there, that all this amazing advancement that he was citing in the talk, none of them actually even mentioned syntactic trees. And syntactic trees, which I extensively studied in linguistics, there are people who did their whole career around this subject. None of these representation are actually essential today for the top performing systems. And it's not only the case in linguistics. I will show later in my talk in chemistry. There is a similar story. A lot of chemical knowledge and the way we are thinking of characterizing chemical properties, they are not part of neural models which are outperforming human chemists. So the question is, what can we extract or what can we learn from what this model produce? And there are a lot of work on interpretability, but assuming that machines becoming really better in extracting very complex patterns that we cognitively cannot really maybe understand, what it would mean to make their reasoning interpretable for us. And I would just want to finish it by the system, by describing like experience that I had with a human doctor. We deployed a system which can look at the images and predict the likelihood of getting breast cancer in a very short while. And it works better than humans, but it cannot explain itself. I mean, you can do, attention, you can do heat map, you can do a variety of things. And the reason is it's not because the system is not okay, it's because humans are not, I think, sufficiently evolved to understand these patterns. And the question that I'm asking myself is how moving forward when these machines become really much more evolved in their ability to abstract patterns, how it's going to connect to our ability to understand stuff.
Okay. Well, I understood the original question as what is wrong with the current hype on deep learning. And my answer to it is that I think intelligence is not only an engineering problem, but also a scientific one. And there are many ways to say that. One is that there is too much engineering going on in deep learning and too little science going on in machine learning and neuroscience of learning. So let me unpack what I mean. First of all, I believe that the problem of intelligence and the problem of learning is really at the core of intelligence, is the greatest problem of science and technology today. It's not one of the greatest, like the origin of the universe or the origin of life, is the greatest of all. And we can argue about it, but that's what I believe. And in addition, it's not one problem, but like biology, is many problems. And so I think we'll need several breakthroughs, one of which is deep learning, another one is reinforcement learning. We need many more if we want eventually to solve the problems of intelligence and build intelligent machines and understanding how the human brain produces human intelligence. So I think that if you look at past history, the main recent breakthroughs were, deep learning and reinforcement learning, and they both come from neuroscience. My personal bet is that several of the future ones will be inspired also by neuroscience, which is science, if you intend with science, the study of natural things like biology, chemistry, physics, and so on. So I hope there will be more science and mathematics of learning, not just running big and expensive GPU clusters.
So does anyone want to take a second stab at this?
I'd just like to amplify the comment that actually tied into the first two talks, which had to do with a new style, if you will. I think that what's been very successful in the 20th century was physics, where you write down an equation in continuous variables and you find ways of solving it, like the heat equation. And I think, though, that these are relatively low-dimensional problems. But, the world is extremely high-dimensional. And I think that what we're beginning to explore is the mathematics of high-dimensional spaces. So when NIPS has been going, was mentioned several times, for over 30 years, and in statistics at that time only looked at small problems with a few parameters, and they could prove that they converged, and they proved that certain bounds and so forth. And we were told we were crazy because we had 1,000 parameters, right? I mean, the early neural networks were really very, we're extremely small by today's standards. And we were told that these learning algorithms would never converge because of local minima. And what was missing was a real sense of what high-dimensional spaces look like. There are no local minima up at the high end. They're all saddle points. And again, mathematical insight in retrospect makes that obvious. But I think, though, that we're just beginning the exploration. High-dimensional spaces are the final frontier. We're living in a high-dimensional world, and I think that it's completely a new place to think about algorithms, and this is, I think we're just taking our first few steps. And so I think that these examples of how these relatively simple deep learning systems are able to outperform humans basically is just telling us that there's information in those inputs that you can extract that aren't obvious to us by just looking at it or reducing it to a few variables that we can then fit approximately. Same thing with linguistics. Chomsky's syntactical grammar, it was an attempt to try to come up with a simple mathematical recursive grammar to explain how we use words. But it totally failed when even tried to parse sentences using computational linguistics. It wasn't until you had large corpuses and you actually extracted neighbors of words, as we heard from Chris, that we began to see the power of high-dimensional spaces. And I think that this is just the very beginning, the very first few steps.
I'd like to put in a word or a plug for both symbolic systems and not. Yes, high dimensions are great, but I'm not sure it's going to do everything. I think we got a little spoiled when we got rid of the human-engineered feature detectors in voice or transliterating speech to text. But I think there's still a place for the human engineering, and I'd like to give an example where deep learning, we could have a tremendous amount of data, but I don't think anyone would want to trust a deep learning system to do this. Microsoft could put in a little tweak and have every instance of every spreadsheet sent back to Redmond, and we'd have a tremendous database of spreadsheets. Then we could build a deep learning system which learned how to operate spreadsheets without actually having to fill in all the little squares and say what's related to what. We could just use deep learning to do that. And I wonder how many people here would like their paycheck generated, unless you're a gambler, from a spreadsheet that had been trained in that way. I think built-in stuff still has a place for some things. We shouldn't, think, oh, it's all gone, it's over.
Labels, what are labels? Labels are symbols. That's one way of putting a symbol in, but you're absolutely right. They are very powerful, and giving them internal structure, I think, was a huge step forward. And a lot of human knowledge, it really has a similar power that can be embedded within the architectures. And I completely agree that the inductive bias that we put into the architecture is really where the exploration is going on today, the hyperparameters. And that's the research in that is really moving very quickly. As there's AutoML now from Google. I'm not sure how good it is, but there'll be other approaches that will be, I think, very powerful.
Professor Barzilay, did you have something you wanted to say?
Okay, so I want to get back to another point which was sort of discussed through the Chris's talk about the supervision and the quality of supervision. What happened today that in order to train a normal size deep learning system, you need to have a lot of data. And for many tasks, you don't have this annotated data. Let me give you a specific example. Because of fake news, there is a data set in NLP which is called Fever, where the system is provided with a claim and an evidence, and you need to induce automatically whether the claim supports the evidence. And the idea, if the system really works, we can just put it on top of Google News and get all our news to be not fake. And the interesting part is that our community works very hard to improve the numbers on this important task. And one of my students who was trying to also improve those numbers actually tried to run an experiment where he just removed the evidence. He just ran the system on claim alone. And this shouldn't work, correct? Because you're validating it in context. And guess, it worked almost as good as a top-performing system. And the reason it happened was an artifact how the data set was created. The data set, in order to get this, huge amounts of annotation, which obviously you cannot collect with highly paid annotator, you use crowdsourcing tools. And for crowdsourcing, when they were creating this fake claim, the easiest way to do it was just add negation to the original claim. So pretty much what the system which was detecting fake news doing was not validating facts, but learning to detect negations. And it becomes better in it. But the problem is that there are more and more papers that demonstrate that when we are looking at all these inference data sets and other crowdsourcing data sets that have been constructed, sometimes our system not becoming more intelligent, but due to the bias that we introduce in the data set, they're actually learning something else. And sometimes the creators of the data set are even not aware of this bias. And I think this is a question, again, the need in data set, it continues to be there. And the question is, what do we do about it? So my student solution was, let's just debias our learning model and see that we know that there is this problem in the data set and we can try kind of to work around it. But there are lots of systems where we are not even sure what is a bias based on what it was trained, and I think it's something that we need to be, thinking a lot about.
Professor Poggio, I'll give you the last word.
Well, one aspect which is not always present in all applications of deep learning, but it's certainly big data. The bigger your training set, the better. And this is not very compatible with how human intelligence develops in a child. We'll never get 1 million labeled examples, with feedback from their parents. If we want really to understand and reproduce learning like our learning, human learning, the interesting limit is not n going to infinity, where n is the number of labeled data, is n going to 1. That's the challenge, really. And until we have done that, we are not going to be able to pass a Turing test, which is really a definition of human intelligence. And, you know, I wonder also the wonderful talk of Chris Manning about translation and language. You know, can this be the explanation for how we humans learn a language? I don't think so, just simply in terms of how many data you need. So there are other ways to do this. And for language, arguably better ways.
Could I add a footnote? Okay. So, you know, this is not the last word. We're coming back. This is no. This is a historical note, which is that for some reason everybody is ignoring everything that came before 5 years ago, as if that was, you know, students especially. And I just want to put in a plug for HMAX, which is something that Tommy Poggio worked on for, you know, decades, which was basically a precursor. And, you know, I think you should be given a lot of credit for being able to show how you could build that up and how the performance compares at monkeys, for example. And I've actually written a book which summarizes that history, if anybody's interested, MIT Press, the Deep Learning Revolution.
Let's thank all our speakers this morning and the panelists.